Good afternoon, everyone. Today I will talk about the groundwater modeling in Guantao. My talk will include the following part. First, I will give a short introduction about the principles in groundwater flow models, and followed that is a detailed introduction about the hydrogeology information in Guantao, and then I will show how to conceptualize the model and how to develop the numerical models, and also show the result. After that, I will show how to apply the numerical model in real applications. Now, first, let's look at what is a groundwater model. Groundwater models are used to represent the real behavior of the aquifers. So we use the numerical models to predict the groundwater level dynamics in time and space. The groundwater movement in the aquifer is influenced not only by the structures or deposit of the aquifers, also influenced by all the processes happened in this aquifer, like the precipitation, evaporation, and interactions with rivers, transpiration, piping, irrigation, and so on. So in order to better describe the groundwater movement in the aquifer, we need the groundwater flow equations. And in hydrology, the basic rules used is mass balance and the Darcy's law. Based on these two principles, we can easily get the groundwater flow equations. And this is one I think everyone is familiar with it. When the derivative of the groundwater level with the time equals to 0, we say that this is a steady state. That means the groundwater level won't change with time and in space. That means everywhere, anytime, the groundwater level are the same. And in order to solve the groundwater flow equations, we need the initial conditions, the initial groundwater level distributions, and also the boundary conditions. There are three types of boundary conditions. The first type is the so-called specified head boundary. This is like the rivers, lakes, which are well connected with the groundwater level or the drainage or spring areas. And the second type is the specified flux boundary conditions. And this is like in the water divide, there's no flow in the model, and all the groundwater lateral recharge from the mountainous area. And the third type is the general head boundary condition. It is a mixed boundary condition of the first two. And the example is like the leakage from aquitide on the boundary, on the model boundary. So the solutions of groundwater flow equations has two. First, it's an analytical solution. This will directly solve the mathematical equations with this initial condition and boundary condition. And these solutions are really accurate, like the Tessy equations, what we used in hydrology. This is a typical analytical solutions. And these analytical solutions could only solve the simple problems. When the real applications become more complicated, like the irregular horizontal shape and the thickness of the aquifer changes, the non-homogeneous of the aquifer, and we need to use the numerical solution. And the numerical solution is an approximate solution. It tries to replace these continuous problems with a discrete problems. The numerical solutions is much more powerful. It can solve all the problems which cannot obtain from this analytical method. And for the numerical solutions, there are also three different types. First, it's the finite difference. Second is the finite element, and then it's the finite volume method. And the finite difference method is quite simple and easy to understand. So it is really recommended for the beginners who just start to use the groundwater numerical models. And the only inconvenient for the finite difference method is because that he can't really or clearly represent the line boundary, like the model boundary or the rivers. because the boundary after this discretization, and this is become this zigzag line shape. So, and for the finite element, because the calculation node is exactly located on the line, so he could really clearly or accurately represent these line boundaries. And the finite volume is more flexible. It is more flexible than these two methods, and it is built up a small finite volume over this computation node, and based on each finite volume, and we can make this mass balance analysis. And nowadays, there's a lot of groundwater modeling software available, and the most common one is the ModelFlow, which is a free software everyone can easily access and download to use. And all the rest of the softwares like the Visual ModelFlow, MikeShe, and they are the commercial software, so you have to pay for it. And since you have to pay for it, then there's also an advantage of such commercial softwares, because they have a nice friendly interface, and they are also well coupled with the ArcGIS, so you can easily import all your ArcGIS products into the groundwater model, like the where locations, the line shape finds, the polygon shape finds. You can directly import it in the groundwater software, and this will really facilitate your pre-processing process. And all these softwares were following the following steps to develop the numerical models. First, you have to collect all the data which is relevant to develop the numerical model, like the groundwater level data, river runoff, precipitation, pumping, and so on. And then you have to conceptualize your aquifer systems. So you have to define your aquifer structure, and to know that where to put your irrigation and where is the pumping happened. And after you collect all these data, and you have to input your parameter values and the real data in time and space for your pumping or the precipitation, and then you input the boundary values and the initial conditions. And of course, you have to also input your observation data. This is important to calibrate the model. And after that, then you discretize your model. That means you will convert all the data that you collected into values on each grid. And after that, you have to adjust the parameters to calibrate your model, and then to get a reasonable result. And based on this reasonable or acceptable numerical model, you can do some applications and to assess some scenarios. And the groundwater models is widely used in hydrology, and is mainly focused on the quantity analysis and also quality analysis. It will identify the aquifer parameters and to understanding the function of the aquifers, and also to evaluate the measures what you implemented at the moment. And of course, you can also use the groundwater model for forecast to predict the groundwater level changes and the climate changes, and other policies. And now we look at the hydrogeology of Guantao, and Guantao is located in the south of the North China Plain, and it only occupies 4% of the whole area of the North China Plain, so it's quite small. And the only surface water is the Weiyun River. It flows from the south to the north on the eastern boundary of the Guantao. And there's also a Weixi Canal. This is in the middle of this Guantao County. It will divert the surface water to the irrigation land. And this is the hydrogeological cross sections of the whole North China Plain from the west to the east. So it clearly that when close to the mountain area, the quaternary deposit consistent mainly of the sand, and when come to the alluvial plain, and then the interbedded layers with clay or the silt shows up, and when comes to the coastal areas, and the deposit becomes finer and finer. Our study area Guantao is located in the alluvial plain. So according to the hydrogeological report of these areas, and we simplified the aquifers in Guantao into shallow aquifer, deep aquifer, and in between there's also a thick aqueduct, which is separate the deep and the shallow aquifers. The shallow aquifers had the bad water quality, so it cannot meet the drinking water quality. And the water in the shallow aquifer is mainly used for irrigation, because the precipitation in Guantao is only about 500 millimeter per year, and Guantao is really important agricultural land. Every year he cropped the winter wheat and the summer maize, so it's a double cropping types. So he need more water. So this is more irrigation waters we are pumped from this shallow aquifer, and the shallow aquifer will also receive the recharge from the precipitation and the irrigation backflow. And the groundwater evaporation is ignored because the groundwater taps in Guantao is much larger at the moment. And the deep aquifer is also quite large, and the TDS in deep aquifer is less than 1 gram per liter. So this is really the good water quality. And the deep aquifer only receives the lateral leakage from the shallow aquifer because of the geochemistry component from these two aquifers are quite different. And also the groundwater level in these two aquifers are quite different. So based on this and also other analysis from the hydrogeological report, and we think that there's only lateral leakage from the shallow aquifer. And in the shallow aquifer, where the groundwater quality is much saline and which cannot use for the irrigation, and in that area we still pump the groundwater from the deep aquifer for the irrigation. But recently, most of this pumping from the deep aquifer is replaced by the surface water. And for the deep aquifers, since the water is non-renewable, and there's only one way to stop the groundwater level decrease. That means to stop this groundwater pumping from the deep aquifer. So based on all of these factors, and in our study area, we only focus to model the shallow aquifer. And like what I said before, and the mainly irrigation is from the groundwater pumping, and also part from this surface water diversion. And plus the irrigation, all the waters will go through the unsaturated zone and recharge to the aquifer. And for the aquifer, of course, we will pump out for irrigation, and we will also receive a bit of a canal infiltration, and also some lateral exchange between the aquifer in Guantao and the aquifer outside of Guantao. And for the aquifer movement in the soil column, we will simulate it using the Hydros 1D software. And for the groundwater flow model, we will develop in the visual model flow flakes. And the model area is the Guantao. And the data we collected is the point data like the pumping wells, locations, pumping rate. Lines data is like this canals, infiltration areas is like the irrigation locations or precipitation locations. And we have to find this model structure. And the surface or the top elevation we download from this from this website. We use this remote sensing data. It's for free. Everyone can go this website and download. The resolution is about 90 meters. And the bottom elevation, and we use the result from the hydrogeological report. And the parameters we used in this shallow aquifer is hydraulic conductivity and the specific yield, and how to divide the parameter zones. And we also, according to the hydrological report, where they did some pumping tests. And the boundary conditions, since the Guantao's boundary is a non-natural boundary, it is administrative, even though there's a Weiyun River. It flows on the eastern boundary of the Guantao, but there's no direct hydraulic connections between the river and the aquifer. So we can't simply use the river level at the boundary conditions. Now we choose observation wells around all the boundaries to interpolate the values on the boundary at the specified head. And the source is the precipitation, infiltration, and the irrigation backflow. And for this number, we use the infiltration ratios to get the groundwater recharge, and for the temperature changes, and we will calculate with the hydros, which I will present in the later slide. And for the canal infiltration, we simulate in the river package, and you need to input the river level in the canal, the bottom of the canal, and the thickness of the riverbed, and the width of the canal, and also the conductivity of the canal. And for the pumping rate, and we simulate in the well package. After input all the data in the model, and we need to discretize the whole model area. And here in the visual model flex, and it has the finite different method, finite element, and also this unstructured grid method. So here we use this unstructured grid finite volume method to develop this numerical model. And for the initial conditions, and we use the result from the steady state model, and later I will also explain the data about the steady state model. And the whole model period is from the beginning of 2003 to the end of 2012. So because we don't have the initial conditions, and we want to find a period, over that period, the average groundwater level should be as close as possible to our initial groundwater levels. And based on this, that means we need to find a period where we can assume that the inflows to the aquifer equals to the outflow from the aquifer. And after analyze the groundwater level changes, and we choose the period from 2003 to 2011 at the period what we will use the average data for the steady state model. And the steady state model we use to calibrate the hydraulic conductivity and the infiltration ratio, and the transient model we can use to calibrate the specific yield. And here we use the hydros model to calculate the temperature changes of the groundwater recharge. Because we don't have any information about the unsaturated zone, includes the soil properties, and we have no observations about water content in the unsaturated zone. Here we use the hydros 1D because we already get the infiltration ratio from the steady state model. So we know that how much water recharged to the groundwater. So this is this part, precipitation plus irrigation multiplied by the infiltration ratio. And we think this is a groundwater recharge. And we know that we put on the top of the surface. And we use hydros model only to simulate that the temperature changes of the distribution of the recharge. And this is the interface of the hydros 1D. It's also an open source software. Everyone can download it. You can define your geometry, define your soil properties, and also the boundary conditions. And here we discretized the soil columns into 100 layers, and every layer has 20 centimeters. And this is like this. This is a zoom in figures. And the boundary conditions, top it's atmospheric boundary, bottom it's a free drainage. And for the model parameters, since we don't have any information, so we assume that the soil is uniform. And the parameters we also adopted from some literature. They conducted some experiment in the Hebei province. It's close to our study area, but it's not exactly the same. But we have no other choices, so we accepted that parameter values and the simulation period for the hydros, it starts from 1980. The reason why we choose this a longer calculation period, because we need a spin-up period to get rid of the initial conditions influence, because we don't know that the initial water content distribution. So we need to have a longer spin-up period. And after we prepare the model, and we have to calibrate it. So the calibration process is also simple. It tries to minimize the difference between the calculation and the observations by adjusting the model parameters, or the way how did you conceptualize your model. Since you get the result from the numerical model, and you can compare from the observations you collected, and then you compare the errors. If the errors is small, you accept it, then we stop it. We stop calibration the model. And if the result is not acceptable, or the errors is too large, and you have to think about it. If you give the right numbers for the model parameters, or you have the right conceptualization process, or you're missing some hydrological process, so this is really a repeat process. You have to repeat it until you get the reasonable result. And this is the result from the steady state. And this is a correlation coefficient between different parameters. And you could say that there's a high correlations between some parameters. That means for these parameters, we can't uniquely determined by this traditional numerical model. Because when you increase one parameters, decrease the other parameters, and you get the same result. And in order to solve these non-unique problems, and I will give the talk about the real-time modeling on the next Monday. If everyone interested in this, we can see each other on next Monday. And this is the result from the unsaturated zone. And this is a blue line. This is a groundwater recharge. This is what we put on the soil surface. And this is the orange line. This is the recharge flux and the soil depth of 2 meters. And this one is 6 meters. The purple is 10 meters. And the black line is about 20 meters. So from this, we can easily observe like these peaks. With the increase of the soil depth, the peaks are also damped and also delayed. So that means the soil columns will damp and delay the water movement from this precipitation and irrigation. And from this, we can say that at the depth of 20 meters, the dynamics, it could steer a bit dynamics, not so dominate like at the depth of 2 meters, but you could still observe it. And this is really varies from the different locations. So that's the reason in the Guantao, and we conducted the hydros models for each townships. So we run 8 different hydros models to get this recharge flux. And this is the result from this transient model. And this is the result for the hydraulic conductivity and the specific yield. And we can see that from the south to the north, and the parameters decreased, and there's also an impermeable zone between each other. And for the infiltration, the large numbers is located in the east, And when it comes to the west, the infiltration ratio becomes smaller. And these numbers are acceptable and comparable to the hydrogeological investigations done by the local partners. And this is a water budget from the groundwater numerical model. And the bar shows this groundwater recharge. And this is, we know that from the hydros models, the changes is not that dominant. So that means the groundwater level in Guantao is this black dashed line, is mainly influenced by the groundwater pumping, is this is a dot line. So when the groundwater pumping is smaller, the groundwater level is higher. And then when it's higher, then it's lower. So the dynamics of the groundwater level is mainly dominated by the groundwater pumping. And we also look at the lateral fluxes exchange between the aquifer in Guantao and the aquifer outside of Guantao. And because the Weiyun River on the east boundary of the Guantao is not explicitly simulated, so it is implemented in the boundary conditions. And the total lateral flux included the Weiyun River is about the 10% of the total inflow. So that means the actual lateral flux exchange between the aquifer in Guantao and the aquifer outside of the Guantao is much less than this 10%. This is also further confirms that in the box model, what Dr. Wang just introduced, could neglect these lateral fluxes in exchanges. And with the numerical model, we can also get the groundwater flow field. And this is a groundwater contour map and the last time steps. We can see that on the east boundary, the groundwater level is high, and the groundwater will flow from the east to the west to the southwest, where the groundwater depression cone occurs. And at the bottom, we showed the groundwater level fitting curves. And we can see that our calculations can really good capture the dynamics of the real observations only at these locations. This is located in the south of this Guantao, is close to the depression zone. And we can see that at the beginning, and there's a large deviation between the computations and the observations. This is because that we use a steady state result at the initial conditions. So that means at these areas, the steady state assumption is inconsistent with the reality. But after 2 years, and we forget the influence of the initial and then the rest, the groundwater model could really good represent the observations. So based on the result, and we think that our numerical models is reasonable now, is acceptable. Now we can use for the application. Could we directly use this numerical model to assess the different scenarios? Why do we need to question ourselves? Because in Guantao, the model boundary is not a natural boundary, and it is an administrative boundary. That means the groundwater level in Guantao are influenced by not only by the inside drivers, also influenced by the outside drivers. So one may argue that, we can find a larger area with the natural boundary, like the North China Plain. As what I mentioned, the Guantao only occupied 4% of the whole North China Plain area. Is quite small. So it is infeasible for this small area, and it's not necessary to build up such large model. And from the large model or the whole North China Plain, the Guantao area maybe only contains 4 or maybe several grids. So the accurate can't satisfy the Guantao's analysis. And I still like to compare this the aquifers with this bank account. and which Wolfgang introduced on Monday. So when the aquifers with a non-natural boundary, this is like you have a shared account with someone else. So if this month you try to save a lot of money, but at the end you saw your account budget and you realize that there's nothing left. Or you may have a luxury life in this month, but at the end you look at your bank account, there's still more money left than what you expect. So in any of these conditions, and we would wonder what is happened. And this is the same for the Guantao's aquifer. And we need to know who influence or which contributions dominate the groundwater levels in Guantao, and how to decompose the influence from the inside and outside contributions. And we need, because we are introduced numerical model, so we can easily to separate the influence using the different numerical models. So the groundwater level in Guantao is can decompose it into the groundwater level changes due to the inside drivers in Guantao, plus the groundwater levels determined by the outside drivers. So for this, we can use this Guantao model, and for the delta H changes, and we need a large model. And for the groundwater level determined by outside drivers, and we also need another model, and but without considering the source and the sinks inside of the Guantao. It only consider about the drivers happened outside of the Guantao area. Now, first we look, in order to solve this numerical model or develop the numerical model, so we also need to understand the groundwater flow equations. And the first one, this is the groundwater flow equations for the shallow aquifer. And here we know that this M, this is aquifer thickness. It's also a function of H. So it is nonlinear. And here we make assumption that the groundwater level changes in delta H is much smaller than the thickness of the aquifer. If we meet these assumptions, we can move the M outside of the bracket, and then we get this groundwater flow equations for the groundwater model. And someone may be questioned that your groundwater decreases so fast, you can't meet this assumption. But since this is a numerical model, so you can also decretize your time step as small as possible. So that means you definitely could find a smaller time steps there. You can meet these assumptions. And then we replace these equations and in the groundwater flow equations, and we get the other two equations. And these one equations we used to develop this large model. And here we need to consider about the sources and the things happened in Guantao. And the other is we used to define the groundwater level determined by the outside drivers. So this equation is easy because we only focus on these Guantao areas. So that means in these Guantao areas, the sources or the outside drivers is located outside. So it's not located inside. So this one will be easy to develop the numerical model. First, we look at how did we choose this large model. And we need to find a boundary which is far as possible from the Guantao. That means all the forces or the pumping or the irrigation happened in Guantao won't influence this boundary. So that means the changes on this boundary is close to zero. And we also use this unstructured grid to discretize the whole area. And inside the discretization, it's the same as the Guantao model. And the boundary condition is zero, and the parameters we need also the hydraulic conductivity and the specific yield. And inside of the Guantao, and we use our calibrated values. And outside of the Guantao, because We don't know the data, but I adopted from this literature. And for the pumping and the canal infiltration and also the precipitation infiltration and irrigation backflow, they are also the same, exactly the same as what we implemented in the Guantao model. Also the stress period is the same. After run the model and you will get the result. This delta H changes at the last time step. And from here you can see that when it's far away from the Guantao and the changes are there. So this is also confirms that the boundary water we choose is large enough. And there's also another point I should mention that because here in this large model for this Guantao area, the boundary conditions is specific, is like the specified flux boundary conditions. But in the Guantao's model, we use these specified head boundary conditions. Due to these different boundary conditions, the distribution of the head changes were also not 100% consistent with each other. So for this consistency, we need to update the delta H in Guantao area. How to do it? And we just extracted the delta H from this large model and to put in this Guantao's model or Guantao's areas model. And we use the same like what we explained in the large model and to rerun this model to update the delta H. And for this outside Guantao model outside, so because we only focus on the Guantao's area, so the model area is the same like the Guantao model, and the parameters is also the same like the Guantao's model. The only difference is the boundary conditions. Because we know that the delta H from the large model, we also had this observation data. And use the observation data minus the delta H, and we can get this groundwater level influenced by the outside drivers on this Guantao boundary. And the source and things like what I said, because for this model, we just want to determine the groundwater level influenced by the outside drivers, the outside precipitation, the outside pumping rate. So that means the sources and the things is located outside. But because we are interested only in Guantao's area, so there's no drivers here. And after we run these 3 different models, then we can get our result. And this is a groundwater level contour map from the groundwater model, and this is the delta H, and this is the H outside. And from this, we can see that the groundwater depression cone is only dominated by the inside drivers, which is influence this delta H. And of course, here we use the 3 different models, and we only have 3 different variables. If we know 2 of them and the other, we can simply use the simple equations to get it. Don't need to run the model again. But for the real applications, we normally focus on time period. We want to know in this time period how much groundwater level is decreased. And based on this, because we can get the equations or we can decompose the groundwater level at any time into the inside contribution and the outside contributions. And if we subtract these 2 equations and use the following 3 equations to replace the corresponding component, and we will get these equations. And this is the groundwater level changes in delta T. And it could be decomposed into groundwater level changes due to the inside contribution and the groundwater level changes due to the outside contributions. And each part we can also get to the result from the 3 different models. And in this case, the time period is 10 years. So here, after running the model, and we get the changes over this 10 years. And this is the groundwater level changes over the 10 years. If we only look at this, and we say that, oh, the groundwater level changes so nice. There's no depression zone is observed. But if we look at these strata changes, you can see that there's still a large depression zone could be observed. That means in the last 10 years, the groundwater level is continuous decreased. And why here we didn't observe this? This is due to this outside contribution, because the groundwater level changes due to these outside drivers is increased in the past years. So this is compensate of the decrease of the inside drivers. So that is the reason if you only look at the groundwater model of the Guantao, and you can't observe this true decreasing zones or depression zones. And now we look at a specific location, and this is the locations in the north of Guantao, and this one is in the south of Guantao. And from here we can see in the 10 years, the groundwater level increased a bit. So you will be happy if you only look at this. But if you look at the strata age changes, that means here it is still a bit decrease. It's not really completely increase. And this is due to these outside contributions, because the groundwater level determined by the outside drivers is increased. So that means for these north locations, and the groundwater changes is mainly dominated by these outside drivers. But if you look at this point, you could say that the groundwater level changes in the past 10 years is about 1 meter. It's decreased by 1 meter. And this is due to this dramatically decrease of the delta H, and also dramatically increase of the outside drivers. So that means the groundwater level changes in the south locations is dominated by both. So the inside of the outside drivers contribute more or less the same effect. And in order to better understand why do we need to decompose the influence, and here we compare to scenarios. These scenarios we just increase the pumping rate by 20%. All the others pumping precipitation or parameters is exactly the same. We didn't change. The only things changed is the pumping rate. And we compare to the present situations. And this is the result for this from these 3 different models. And I also choose these 2 different locations. Of course, and when the pumping rate is decreased, and it doesn't matter for the Guantao model or the large model, you could say that the groundwater decreasing rate is decreased. So if you look at this, and then the north point, the groundwater level changes is about 4 meters, and then decrease to the positive 1 meters. And the delta H is also decreased. And this is the same for the point in the south. But this is not the point we want to stress out. We want to stress out, even though we decrease the pumping rate by 20%, and if we only look at the groundwater, the result from the groundwater model, and we see that, okay, the groundwater level now is increased. So we are satisfied with the measures, what we implemented at the moment. And but if you look at the delta H, you decompose the influence, and you will see that there's still a slight decrease in rates happened in the north of the Guantao area. But if you look at the south areas, so here you are also be satisfied if you only look at the result from the Guantao model, because that the decrease rate is about 1 meter in 10 years. So you are positive. And the question that should we stop here, or should we continue to find a better solutions to stop the groundwater pumping? If we only look at the result from the groundwater model, maybe you stop here. You said that our scenarios or our measures in water resources management is acceptable. We are positive to it. But if we look at the result from the large model, you realize that in these areas, the groundwater level is continuous to decrease and is about half a meter per year in the last 10 years. This decreased rate is still large. So if you look at this, you will know that, oh, we can't so positive to our measures. We still need to continue to decrease the pumping rate or to find other solutions to replace the pumping rate. So based on this, so we want to mention that for the numerical models which don't have these natural boundaries, like the Guantao areas, we need to separate the inside and outside contributions to better evaluate your scenarios or to give a reasonable information about how to manage the groundwater resources in future. If anyone is still interested in some detailed information or some other sensitivity analysis about these decomposing techniques, you can download from this link to look at these papers. All the result is online now. Okay, this is what I talked today. Thanks for your attention.